Yeah, let's continue. 25 more minutes. Okay, I will stop the class at 10:50. So we were talking about this example, and sometimes of in different way you can do this, but I suggest you always in this kind of system use Gauss-Jordan elimination methods, and also get used actually to use methods. So here, as you see here, if you just multiply the second row by -1 and add to the last row, here we will have 1 and here we have 0. So here we will have, what is it? 1, 2, 1, 2, 1, 1, and 4 minus 1, 1. And here we have 1, 0, 0. So now I'm going to write the last row at the top. As you see here, other components are 0, 0, and multiply by -1. And we can create 0 above this, right? So here we will have 1, 0, 0. So all of these numbers will be 0 because multiply by -4 and add to the third row, multiply by -2, add to the second row. And just in a similar way, we can create 0. So here we'll have 0, 2, 1. And the next one is 0, 1, 1, 0, 1, 1. The last one is 0, minus 1, 1. And also, as you see here, the third line and fourth line, right? If you just add the third row to the fourth row, here we will have 0, and here we have 2. Again, multiplied by 1/2. Here we will have 1 again. So in this way, I can create 0, right? Here we have 0, 0, because just multiply by -1 and add to the second or third row. And also here we can create 0. So that means that, what is it? Here, the solution of this system is x is equal to 0, y is equal to 0, and z is equal to 0. So the only way we can write the linear combination of these three matrices where the sum equals 0 is when x equals 0, y equals 0, z equals 0, which means that it is a trivial solution, right? That means that these matrices are linearly independent. Okay, so that means that we cannot write any of these matrices as a linear combination of the remaining matrices, or simply they are linearly independent. The next question, here we have proved the theorems 3.2 and D and the E and H. Actually, all of the theorems are proved in the video. I'm not going to prove them here. And let me just do only 22. It is simple one, just I want to draw attention to, again, this property. We know that A times B is not equal to B times A, especially students, if they are learning or studying matrices for the first time, they confuse this property a lot. Okay, why is this so? So here, prove that for square matrices A and B, AB equals BA, BA if and only if A minus B times A plus B equals A squared minus B squared. Okay, again, this if and only if. That means this one is I, F, F. This means that it is if and only if. So it has two-way implication. What does it mean? Here, this implication, that means that if AB is equal to BA, then we have to show that that is true, okay? So how are we going to show that it's true? So since I know that AB equals BA, then A minus B times A plus B is equal to, multiply from the left-hand side. Okay, you should be careful when you're doing this multiplication, because multiplying the matrix on the left, on the right, these are different things. It's not like real number system, right? A times A, so here we have A squared. A times B, so here we have A, B, minus B times A, that is minus B, A, and minus B times B, that is minus B squared, because A times A defined as A squared. Now, immediately, you can see that actually AB is equal to minus B is equal to 0. It's not equal to 0 because we don't know this A, B, and B are equal. Generally, they are not equal, right? Because the matrices do not have commutative property under multiplication. So, but here, we know that here in the question, it's given. If I suppose that AB equals BA, At the time, these two things are equal. So they actually AB minus BA equals 0 matrix. So here we have A squared minus B squared. Okay, if you subtract again, we don't get 0, we get 0 matrix, and their orders are the same. Okay, so now how about this? Because if and only if means now I have to show that if this statement is true, now I have to show that then AB must be equal to BA. Okay, so suppose that A minus B times A plus B equals, suppose that A minus B and the A plus B is equal to A squared minus B squared. If it is true, that means that if I expand the left-hand side, I get here A squared minus plus AB minus BA plus minus B squared. On the right-hand side, we have A squared minus B squared. Now these two things, they cancel out each other, and also negative B squared, right? And only we have this thing. What we have here? Here we have A times B minus B times A. On the right-hand side, we have 0 matrix, right? So just take this BA to the right-hand side, or anyway, AB equals BA. So that means that if this statement is true, then A times B must be equal to B times A. Okay, that is how, I know you understand this, but this is how we have to prove this kind of statements or properties or formula, let's say. Another question in exercises 23 to 25, if B is this matrix whose components are A, B, C, D, find conditions on A, B, C, and D such that AB equals BA. That means that, what does it mean? Again, here on purpose, they give a few questions so that students should practice and get deeper intuition about that AB is not equal to BA in general. All right, so A is given, right? So we have to show that again here, I will do 24. And I think Yihin already did 23, 25, or maybe he will do later. So let's do this even number here. It's 24. A times B. What is A times B? So A is here 1, negative 1, negative 1, 1. And how about matrix B? It is A, B, C, and D. Equals, how about B? Here we have A, B, C, and D. And matrix A, 1, negative 1, negative 1, 1, right? So actually, with what matrix actually does this A commute with? Okay, that's the question here. So that means that for not every matrix, A times B equals B times A. Under certain conditions, then this AB equals BA. What is this? Again, if you just subtract left, carry out this multiplication, on the left-hand side, we will have A times 1 times A, negative 1 times C, that is A minus C. The second one, 1 times B, negative 1 times D, that is B minus D. The second row, negative 1, so it is negative A plus C. And the last one, it is negative B, negative B plus D. How about on the right-hand side? Here we have A minus B. So here we have A minus B, minus A plus B, minus A plus B. And here we have C minus D. And here we have minus C plus D. Again, we know the two matrices are equal if and only if their corresponding components are equal. From here, we get A minus C should be equal to A minus B. The second one, B minus D should be equal to minus A plus B. Third one, minus A plus C should be equal to C minus D. And the last one, minus B plus D should be equal to minus C plus D. Now from here, from the first one, AA cancels each other, right? What do we got from here? That means that B is equal to C. From the second one, B cancel out each other. So this implies that A is equal to D. And also from this one, CC cancels each other. That means A equals D. And here DD cancels each other. that is B equals C. So what is it? Actually, the matrix A commutes with B if and only if the components or entries of B satisfy this condition. What is it? That A must be equal to D and B should be equal to C. So what are these matrices? This kind of matrices, right? A, D. So that means maybe it's like 1, 1, 2, 2, for example, right? Or -2, -2, let's say 5, 5, for example. Or let's say this 10, 10, here we have 3, 3, for example. Actually, the type of the matrix here, it must be this, right? So if you just pick any, if you're talking about 2 by 2 matrices, so if we are talking about some kind of matrices here, they can commute with A. What are these matrices? They satisfy this condition. What is it? Here we have X, X, Y, Y, right? So that means that is symmetric matrices actually. These are, how do you call this? This 1, 1, 2, 2. That means that these matrices are symmetric matrices, right? Symmetric square matrices. Okay. All right. So this 26, also similar question. In a similar way, you can do that. 27, and that's also similar. Let's just do 28 here, because we should do even numbered questions. So let's do 28 here. It says that prove that if AB and BA are both defined, then AB and BA are both square matrices. Okay. So by the definition of multiplication of two matrices, this AB is defined. What does it mean? Let's say it is C. So if the dimensional size of this matrix is, let's say, M by P, right? And this B must be, it is P by N. Let's say something like this. So actually these two numbers, number of columns of A must be equal to the number of rows of B. So the resulting matrix dimension will be M by N, right? Okay, it is something like this. Okay, now how about BA? And also we are saying that we are talking about the same matrices. If this BA is defined, let's say the year product is equal to D, and then what is the dimension of this B? It is P by N. And how about A? It is M by P, right? Since we are saying that it's defined by the definition, it is must that N must be equal to M. N must be equal to M. So that means that here, again, the resulting matrix will be, what is it? P by P here. And also from here, since M is equal to M, so also the C will be either M by M or N by M matrix, or N by N or M by N matrix, okay? Which means that if AB and BA are defined, that means that A times B and B times A, they must be, what is it? Square matrices. Okay. That is how we prove this. Another thing that we are going to see this more in the next chapter or in 3.4, a square matrix is called upper triangular. And we have unit lower triangular matrix and upper triangular matrix, okay? Unit lower means all the elements or entries in the main diagonal, they are ones, and the entries above the main diagonal, they are zeros. But how about upper triangular matrix? If all the entries below the main diagonal, okay, we say upper triangular means only we have non-zero entries above the main diagonal, but all the entries under the main diagonal, they are zeros. Then we call this matrix an upper triangular matrix. Actually, as I said, the name suggests here that it looks like a triangle. That's why it's called triangle. But which part? The upper part, right? That's why it is upper triangular matrix. For example, for this matrix, when you talk about 2 by 2, 1, 2, 3, 0. This one is upper triangular matrix. How about for 3 by 3? Let's say 0. Let's say it is 1, 3. Here we have 0. Let's see, here we have 0. and here we have 0, 0, 0. Let's say here we have 5. I'm on purpose, I'm just writing 0, just if one entry is not equal to 0, that's enough for us. As here also, this one is upper triangular, because if you just draw the line through the main diagonal, right, all the entries below the main diagonal, they are zeros. Okay. In a different definition, and how can I define this thing algebraically? As you see here, all the entries below the diagonal, right? What is this? This entry is, it's like A21. And how about this entry? It is A31. And how about this entry? It is A32, right? In general, if you're talking about the matrix, let's say whose entries are A sub ij, right? So as you see here, the row index, right, is greater than column index. And also row index is greater than column index. And row index is greater than column index. So also we can just simply define this in this way. A more formal definition of such a matrix A, whose entries are Aij, is that Aij is equal to 0 if I is greater than j. That means that where are these entries? They are just below the entries. And how about if I just call like this, Aij, where actually I can just give definition, later we will see this, that's equal to 1 if I equals j. What does I equal j mean? That means that entry is in the main diagonal, right? Here, A11, A22, dot, 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 and here we have A and M. That means I equal j. I mean, the row index is equal to column index. And is equal to 0 if I is less than j, right? So that means that actually at that time we call such matrices unit triangular matrix. Okay, unit triangular matrix, because all the entries in the main diagonal are 1. Maybe you don't have to know this. We'll talk about this in 3.4. Now our focus is about upper triangular matrix. Okay, because actually this notation is really useful when we are dealing with some problems or proving theorems. Okay, in 29, is there any question here? All right, no. Prove that the product of two upper triangular n by n matrices is upper triangular. Okay. And after that, prove theorem 3.4a to c and prove theorem 3.4e. I think I have already proved this in those videos. And using induction, prove that for all n is greater than or equal to 1, a1 plus a2 plus a is equal to this. Using induction, prove this. And okay, I think most of these theorems I have already proved and shared this. And if you want, we can do this one more time. But now here, guys, let's just do question 29. Okay, as much as we can. We have 5 minutes left. All right, 29. Okay. Assume the proof that the product of two upper triangular n by n matrices is upper triangular matrix. So we are talking about two matrices. Let's say we are talking about A and B. Okay. And I had shown that also their product is C. Also, it is upper triangular matrix. Okay. So we know that the dimension of A, it is n by n. Dimension of B, n by n. More than that, actually it specifies that actually here Aij is equal to 0 if I is greater than j. And also the entries of B, let's say Bij equals 0 if I is, what is it, greater than j. These are given. Okay, this is given information. Now we have to show that also for C, if you just take any entry Cij, we have to show that that's equal to 0 if I is greater than j. Okay, so now by definition, how do we find Cij? Actually, we know that this Cij is equal to this ith row, right, of matrix A, right, times a dot product. Actually, it's just multiplication and dot product. It is J's column of B, right? This is how we multiply. If you're talking about, let's say, 2 by 2 matrices, right? And for example, let's say if we have C11, C12, C21, C22, right? How do I get this C22? C21. C21 means I need to multiply the second row by the first column, right? That is how we get this. And how about C22? We need to multiply the second row of the first matrix by the second column of the second matrix, right? And that is how we obtain, define the multiplication of two matrices, okay? So here, ith row of A dot J's column of B, okay? So here, all right, how many minutes left? 18. Okay, guys, let me stop here. Okay, we have like 3 minutes left. You have class at 11 o'clock. We will finish from here. And I really want to spend more time on proving theorems. Okay, maybe also we can prove other theorems together. So for this week, that much is enough. Focus on your assignment and also start preparing for your quiz. Okay, so we have Telegram. All right, anytime we can exchange our messages so instantly. If you have any question about quiz assignment, anytime you can ask. Okay, so I will meet you on Tuesday. At least actually I will send you, and I will stay online on Telegram during the quiz time. Okay, I'll try to answer questions if you have any problem during the quiz time. Guys, now I will finish this. Okay, this one, if I continue, it takes a little bit more time. So let me stop here. Next class, hopefully we will prove these theorems one by one. Thank you very much. I will see you next Tuesday. Have a nice weekend. Bye-bye.